guys, welcome to our video notes lesson on section 6.5, where in this section we're going to take those logarithmic functions that we've simplified and graphed, and we're going to solve equations that contain logarithmic expressions. So there's two types of situations we might encounter. One situation is where every expression in the equation contains a logarithm. And so in that situation, what we're going to try to do is get it so that there's just one log on each side of the equation, which means we may have to use the properties of logs to condense it, to make it so it's just one log on this side and one log on the other side. So the reason why we want to set it up that way is because of this property right here. So this is giving us what we call the one-to-one property. What this property basically says is that if you have an expression like this where the log of the same base of one input is equal to the log of the same base of a different input, if those expressions are equal, then the inputs themselves must be equal. So these log expressions could be thought of as the outputs, or the y values, if you will, of the log function. So if the two outputs are the same, the only way that that would make sense is if the inputs are the same, because the log function is one-to-one. So just a quick reminder, what does it mean to be one-to-one? Okay, I'm going to use just our generic sort of log base 2 of x to kind of talk about it. One-to-one means that for every single y value on this curve, okay, as I move along the curve, I would have a different x, a unique x. So one x for each y, meaning I could draw a horizontal line through my graph. So I just decided to use y equals 1 here. And it would only intersect that graph one time, meaning it would only have one x, unique x, that matches that y value. And no other y value will have that same x. And I could even change the horizontal line to go through at different points, but it would only ever intersect the graph one time, no matter which y value I chose, etc. I would only ever have one point of intersection, meaning only one input for that output. There's no way I could have a different input that goes with that same output. Similarly, if I pick an x value, maybe I'll pick x equals 1, then that x value, so that vertical line, would only hit the graph one time, meaning there would be only one y value for that input. Each unique input, so maybe I'll pick a different input, would have a unique output. In other words, this line is only hitting the graph once. There's only one y value that goes with an x value of 2. So what does that mean? That means if I were to plug in log base 2 of 5, for example, so that would be when x is 5, I only have this output, 2.32 whatever. But if I were to pick a different input, say 3, I would have a different output. That would be if I had x equals 3. Then I'd have an output of 1.585. There's no way that log base 2 of 5 would equal log base 2 of 3. It just doesn't work. This function is one-to-one. If my input is different, then my output is different. And that is essentially what this expression is saying here. It's saying if these outputs are the same, if I ended up with the same output, you know, whatever crazy decimal output it would be, the only way that that could happen and make sense is if the thing that I plugged inside was the exact same. So that's what we're doing in step 2, is we're setting the inputs equal to each other. We're making use of this fact, this one-to-one property. Okay, so then once we set the inputs equal to each other, we then solve that equation, we then check our answer. The other option that might happen when you're solving a log equation is if not every term has a log. So there might be something in your equation that doesn't have a log. So what you want to do in that situation is isolate the log, meaning there should be only a log on one side, kind of like this, and whatever numbers or other things there are would be on the other side. So you'd isolate the log. And then what you can do is use this fact. This is just the definition of a log, basically, to rewrite the expression in exponential form. That's this one. That's where you take the subscript of the log and you understand that's the base. You take the thing that's inside the log and you understand that that's what the result would be if I took that base and raised it to the power of whatever the log equals. Remember, whatever the log equals is the exponent. So I can rewrite it in that form, and then from there it forms an equation that I can solve, and then I can check my answer. So why don't we start with number 1? So in number 1, I have a situation that matches option 1, where each expression in the equation contains a log. In fact, it already looks like it's in this format. Log base 7 of something equals log base 7 of something else. The only way that that would make sense is if those inside pieces are equal to each other. So I already have one log on each side. I'm just going to go straight to the step where we just take those inputs and we say, well, those must be the same. That's the only way that this could be equal. And then we just solve that expression. So I would solve for x, basically combine my x terms together. I'll add my 5 over, and I get x equals 6. So according to this algebra, what I find is that these two log expressions will be equal if, and only if, x is equal to 6. So let's check. So what I'm going to do is take my 6 and I'm going to plug it back in for x in my original equation. So when I do that, I get log base 7 of 2 times 6 plus 1 equals log base 7 of 3 times 6 minus 5. So then that becomes log base 7 of 13, and then again log base 7 of 13, because that would be 12 plus 1. This would be 18 minus 5. Check. Those expressions are identical, therefore that is true, therefore x must be 6. So in example 2 here, this one matches option 2 because not every term in this equation has a log, and that part that doesn't is the 3. So because the 3 does not have the log, what I'm going to do is get my equation to look something like this, where I have a log on one side and then just the number on the other. So how do I combine these two logs? Well, I noticed that the two logs are being added, so I'm going to use what's called the product property of logarithms. The product property of logarithms says that if you're adding the logs, of course the base of each log has to be the same, which it is, it's 2 in both cases, then what you do is you multiply, right, the product, you multiply the items that were inside the log. So if you're adding the logs, adding the outputs, you combine that into one log by multiplying the inputs. And then meanwhile, I still have the 3 on the other side. So now I have the log base 2 of 6x is equal to 3. So it looks something like this expression here. So I'm going to rewrite it into exponential form. We're going to remember that the base is whatever the subscript of the log is. The inside of the log would be the result, what you get after you raise the base to the power. Whatever the log equals is the power. Remember, the log equals the power. So I know that if I took the base of 2, raised it to the power of 3, whatever the log equals, I would end up with whatever's inside the log. So that ends up being, so 2 to the third just ends up being 8. And then to solve for x, I just end up having to divide by 6. Of course, we should always reduce our final answer. I can divide each of these numbers by 2, which then would reduce to 4/3. So in this particular case, my x value was equal to 4/3. So I should check with the original equation to make sure my answer is correct. So I'm going to plug 4/3 right in here for x to see if it does in fact equal 3. So again, I'm going to use the product property of logs to combine these. So the log base 2 of 6 plus the log base 2 of 4/3 is the same thing as the log base 2 of 6 over 1 times 4/3. So that would be 24 over 3. Because you just multiply the fractions straight across. 24 over 3 is the same as 8. And the log base 2 of 8 does in fact equal 3 because If I rewrite it in exponential form, that would be my base of 2 to the power of 3 equals 8. So that means that my answer of 4/3 is correct. Why don't you guys try number 3? Okay, so when we solve number 3, we end up with x equaling -13. So this was the solution we got from solving this equation here, right? This equation is what we call a linear equation, where the x is allowed to be any real number. However, we have to remember that these expressions came from inside a log expression, but a log expression has a restricted domain. That is to say that their inputs need to remain positive. If you look back at this graph on Desmos, you can see, so here's the equation for log base 2 of x. You can see how the inputs, right, the x values, never quite get to 0 and never quite go to the left of 0. They get close, right? If I go down here, you can see it gets like right up on that y-axis, but it never crosses it. These are showing us the domain. These are showing us that for a log of some function, or a log of x, that x value has to stay positive. So what does that mean for my answer over here? What that means is if I go to plug in -13 back into these expressions, I would end up with the log base 12 of -13 plus 5 on the left equals the log base 12 of 3 times -13 plus 31 on the right. So the -13 plus 5 would turn into -8. And then the 3 times -13, that's -39, plus 31 would also be -8. So you can see how we would get -13 as an answer because it makes the expression on the left match the expression on the right. But the problem is these expressions don't exist. So I can't say that they're equal because these don't even exist, because the number inside the log needs to remain positive. Otherwise, it just doesn't exist. It has no value. So we have to be careful to check our answers, especially if they come out negative. We want to make sure, would that make the inside of my log negative? If so, I actually can't use it as a solution. So that's what we would say for our final answer for this, is that there is no solution. So then moving along to number 4, you can see that this matches more of the option 1 type because each expression in this equation has a log. So don't forget that the ln of x stands for the natural log. So it is a log. It just abbreviated with ln for natural log. But you could also understand it to be a log base e. So it really does follow all the same properties. In fact, maybe I'll rewrite it that way. So this would be a log base e of 4 minus a log base e of x equals a log base e of 36. So I noticed that these logs are being subtracted. So what I'm going to use here is called the quotient property of logarithms. The quotient property says that if you're subtracting two logs, you can combine the logs together, same base, log base e, if you divide the inputs. So subtracting the logs means that the inputs of the logs were dividing. So then I'd get ln, or log base e of 4 over x equals ln, log base e of 36. So I have one log on one side with the same base equaling another log with the same base on the other side. The only way that that could be true is if the insides were equal to each other. So I just take those inputs, I set them equal to each other. I'm going to multiply both sides by x over 1 to cancel out the x in the denominator. So I get 4 is equal to 36 times x. I'm going to divide by 36 to get my x alone. Again, I can reduce this fraction. 4 goes into 36, or you can divide both of these by 36, and I would get 1 over 9, and that is my solution for x. Moving on to number 5, I noticed that this matches more like option 2 because of this number 2 that doesn't have a log. So not every item in this equation has a log, so therefore we should combine these logs together so I can get it to just 1 log on this side equals 2 on the other side. So I'm going to use the product property of logs again because these logs are being added. So I can combine this into 1 log of the same base, base 4, where I multiply the inputs of each log together. By multiplying the inputs of each log, that allows me to combine this sum, this addition, into 1 log. So I'll go ahead and FOIL out the insides of this log. So through FOILing, I get x squared minus 2x minus 8 on the inside. So now I get to a point where I have a logarithmic expression, but remember I can rewrite this into an exponential expression. So let's put a little star by here and write rewrite into exponential form. You're going to want to make a big deal about that on your notes, like put a bunch of stars and whatever's, because this is usually the part where students get stuck. They forget. So when we get to this point where you have 1 log on the left or the right, and then a number on the other side, what you're going to remember is that the subscript of the log is the base. So the base is 4. Whatever the log equals is your power. So 4 is being raised to the 2nd power. And then this part that's inside the log is the result. What you get after you take that base of 4 and raise it to the power of 2. You would end up with x squared minus 2x minus 8. So notice this resulting equation is quadratic. I have an x squared. So what I'm going to want to do, also remember here 4 squared is just 16. But what I'm going to want to do is get 0 on one side. So whenever you have a quadratic equation, what you're going to want to do is get a 0 on one side. So I'm subtracting the 16 from both sides so that I would have 0 equals x squared minus 2x minus 24. Now I have a quadratic equation set equal to 0, which will allow me to either factor and set each factor to 0 or use the quadratic formula. This one will factor though because of -6 and 4. -6 plus 4 would equal the -2, and -6 times 4 would equal -24. So I can take each of those factors and set them equal to 0. I can do this because I got one side of my equation equal to 0 earlier. That allows me to take each factor and set it equal to 0. And when I do that, I get 2 different answers. But you got to be careful. You got to remember that thing about the domain restriction for logs. This is violating the domain restriction for logs. Remember, the inputs have to be positive. So what am I saying? Okay, so let's look back at the very original equation. That was way back here. Let's zoom in on this a little bit. If x is allowed to be -4, then inside this log I would have a -2. That does not exist. And inside this log I would have a -8. That also does not exist. So I cannot let -4 be a solution to this particular equation because, see here, I got -4 because I was solving a quadratic, right? This is a quadratic equation. So quadratic equations are allowed to have inputs that are any real number. That's how I got this -4, but I'm going to cross that out because really this was inside of a log. The x values were inside of a log, and the insides of a log cannot go negative. They have to stay positive. So I only am allowed to have one solution for number 5, and that one solution would be x equals 6. Now in number 6, we have something that actually follows option 2 because of this number 2 right here. It does not have a log around it. So what I'm going to want to do is get a log on one side and then a number on the other. I want to get it to look something like this. So I'm going to have to combine these log expressions together. So I think what I'm going to do is subtract this log base 5 of x to the other side. Because remember, I want to get one log on one side isolated, and then just everything else on the other side. Okay, now here I see a coefficient in front of the log, but I want to condense this into one log expression of 5. So what I'm going to use here is called the power property of logs. Now what that allows me to do is it says, okay, if you have a number being multiplied to the outside of a log, what you can do is take that number inside and make it the exponent of the thing inside the log. So this would turn into log base 5 of 10 squared. That 2 becomes the exponent of the 10 inside the log. And then now there's no number in front of the log. So on the left side I still have the 2. Now here I'm going to use the quotient property of logs because I'm subtracting. The quotient property of logs says that if you are subtracting the logs, what you can do is divide the contents of the logs. So I get 10 squared over x. Maybe I'll simplify that a little bit to just 100 over x. Okay, so now make a big deal about this on your paper because this is the part where I guarantee you're going to be like, wait, what do I do? I'll tell you what you do. You rewrite this expression into exponential form. Okay, you say, okay, 5 is the base, 2 is the power, 100 over x is the result. You rewrite it in that way. 5 squared equals 100 over x, and then it's a piece of cake. 25 equals 100 over x. I need to multiply by x to both sides to cancel it. I'll go this way. So then I have 25x equals 100. And then I just divide by 25 and I get x equals 4. Like from here on, it was a piece of cake. So you just have to remember this. Star that, make it super special so it really stands out and you remember to do this because then from there it's not hard. But you should check, you should take that 4, go back to the very beginning. We're going to check this with the very beginning. We're going to see if a solution if my solution of x equals 4 would work with the original equation. So I'm going to plug in, I'm going to have log base 5 of 4 plus 2 equals 2 times log base 5 of 10. Well, if I'm going to try to check this, I'm going to need to subtract this log base 5 of 4. And I'm going to need to bring this 2 as the exponent again. So I have log base 5 of 4 plus 2 equals log base 5 of 10 squared, which is 100. And then I would need to subtract that log base 5 of 4. So I'd get log base 5 of 100 minus log base 5 of 4. And then I would go, well, the logs are subtracting, so therefore I will divide the contents of the logs, 100 divided by 4. I get 25. So then it's just a question of, does 2 equal the log base 5 of 25? Yes, it does, right? Because 5 to the power of 2 equals 25. So yes, so x equals 4, if I plug it into my original equation, makes the equation true. So let's take a look at number 7. We got a whole lot of stuff going on here. But notice that every single expression here contains a log. So this matches the option 1 style. So what I'm going to want to do is just get one log on each side. So I basically just need to combine these into one log. The right side's already good to go. So I'm going to use the power property, like I mentioned earlier, to bring 2 inside and make it an exponent of 4. I'm going to do the same thing with the 1/3 here. So I'm going to get log base 6 of 4 squared minus log base 6 of 8 to the power of 1/3 equals log base 6 of x. So then I'll simplify those a little bit. So 4 squared is 16. And then do you guys remember what 8 to the 1/3 is? 8 to the 1/3 is the same thing as the cube root of 8, which would be 2, because 2 times 2 times 2 equals 8. So the cube root of 8 is 2. Okay, so then I get 2 here. So again, I have a subtraction of logs, so I use the quotient property to divide the contents of the log. 16 divided by 2. So then 16 over 2, that would just give me 8. So then I have log base 6 of 8 is equal to log base 6 of x. The only way that that makes any sense at all is if x equals 8. If x equals 8, then of course these expressions would be the same. So as has been our custom with our note outlines in Unit 6, we're going to end with finding x and y intercepts now that we're able to do that for all our functions. So just as a reminder, to find the x-intercept, we are going to plug in 0 for y and solve for x. So those are always a little harder because it involves solving, and that's why we had to wait for Unit 6. That's what Unit 6 is all about. To find the y-intercept, we plug in 0 for x and just evaluate y. See, in both of these, or all of these ones, the y is already solved for, right? It's y equals something. That means this is what y equals. We don't need to solve for it. We just need to evaluate, so it tends to be a little easier. So let's start with number 7. For both of these, I'm going to go ahead and begin with our y-intercept just because it's easier. I'm going to start with the easier one. So that is where you plug in 0 for x. And then from there, it's just a matter of evaluating. So 0 plus 5 is 5. So I get the negative log base 3 of 5 plus 2. I know that seems weird, but that is a number. That's the exact form of our intercept. So our intercept would be 0, comma, usually we write it like this, 2 minus the log base 3 of 5, just because it looks a little bit nicer. And we can think of it as a number of 2 being, and then subtracting this decimal. So really quick, if I plug that into Desmos to check, so 2 minus the log base 3 of 5, it's just this number right here, about 0.535. If I look at the graph of this equation, y equals negative log base 3x plus 5 plus 2, and I look at my y-intercept, I see that it does in fact hit the y-axis at around that decimal, because that decimal value came from this log expression. But when you're typing in your answers for like a test or quiz, you want to keep it in this form because this is considered exact. It just helps to kind of have an idea of approximately what that number would equal, so it's not such a strange value. So it's a little close to 1/2, basically. Okay, so now that was the y-intercept. Now what we're going to do is the x-intercept. This one's a little harder. This is where you take the 0 and plug it in for y. So 0 equals the whole equation here. And then your job is to solve for x. So you have to get rid of all these things around the x. So these equations are going to always follow the option 2, where not every term has a log. So what I'm going to do is isolate the log. I'm going to subtract the 2 so it's on the other side. Think of this negative as negative 1 times the log base 3 of x plus 5, and I'm going to divide by that negative 1 because I want to get my log all the way isolated. When you get here, I want you to make a big deal about this on your paper. This is where you rewrite it into exponential form. So you take the base of 3, raise it to the power of 2, and when you do that, it results in this expression, x plus 5. So 3 squared equals x plus 5. Okay, so 3 squared is just 9. See, look how easy it is after you do that. Like, that is the trick right here. Then it turns into like a super easy linear equation. I just subtract 5, and I get x equals 4. So as an ordered pair, that would be 4, 0. So we had 0, craziness, 0, 2 minus log base 3, 5 for our y-intercept, and then 4, 0 for our x-intercept. So I'd like you guys to try for number 9. So for the y-intercept, we would plug in 0 for x. So we're looking for f of 0. That's another name for the y-intercept. So I plugged in 0 for x. So that means inside the log I got 1. So what I want you to remember is that any base, including a base of 1/2, to the power of 0 equals 1. That's one of our exponential properties. So no matter what your base is, if you're taking a log of 1, the value is always going to be 0, because remember the log is the exponent. So log base 1/2 of 1 just turned into 0. So then this 2 times the log became 2 times 0. And then of course that just equals 0. So then I had 0 minus 6. So my y-intercept for this one was negative 6. Go ahead and try to find the x-intercept. So for our x-intercept, we had to plug in 0 for y, and then I had this whole expression over here that I had to solve for x. So I added 6 to both sides to get a 6 on the left, and then a 2 times log base 1/2 of x plus 1 on the right. And then I had to divide by the 2 to cancel it out on the right side, and then I got 3 on the left side. So then I had 3 is equal to log base 1/2 of x plus 1. So then I had to remember that's where I rewrite into exponential form. 1/2 was the base, 3 was the power, x plus 1 is the result, so that's right here. So 1/2 to the third, that's 1/2 times 1/2 times 1/2, that's 1/8. So 1/8 was equal to x plus 1, and then I just subtracted 1 from both sides. So 1/8 minus 1 is -7/8. And so that was my x-intercept. That concludes this video. Thanks for watching. See you in class.